Hello everyone, in this video we'll be talking about the forced oscillation or the driven oscillation and the resonance. Before we dive deeper into the concepts, let me ask you four brilliant questions. Question number 1. Suppose there is a notorious kid and looking at his report card, his father gives him a tight slap and for few moments the vision of that kid becomes blurry. Why does that happen? Or if you might have similar experience, let me know in the comment box why the vision becomes blurry for some moments of time. Second question, while crossing a bridge, the soldiers are instructed to go out of step. Why? Third question, in an earthquake affected area, all the buildings do not experience the equal amount of damage. Why does that happen? And the last fourth question, while driving at a certain speed, the bus or a car or the vehicle produces a vibrating rattle. Why does that happen? Post your opinion in the comment box. Now let's begin. First of all, we'll be talking about the free oscillations, then we'll talk about the driven oscillations or the forced oscillation. Then we'll go into the mathematics of the driven oscillation and we'll talk about the resonance with great examples. After that, you'll get a checkpoint, few solved questions, and finally the answers of all the checkpoints. So this is the outline of the video. Let's go further. Here you can see the heading, the free oscillations. What do you mean by the free oscillation? The answer is simple. Suppose there is a simple pendulum or a spring block system. We displace this spring block system or the simple pendulum from its stable equilibrium position and we release it. It moves to and fro about the stable equilibrium position. This kind of oscillation is known as the free oscillation. Although because of the ever-present damping forces, all the free oscillations finally die out. Clear? Now, we see the next definition, the driven oscillations or the forced oscillation. If we want to maintain or sustain the oscillations, then whatever mechanical energy is decreasing due to the presence of damping force, equal amount of positive work should be done by the external periodic force. Then system can maintain its energy level as well as its amplitude. And then the oscillation is sustained. These kind of oscillations are known as the driven oscillation or the forced oscillation. A beautiful example of the forced oscillation is this pendulum clock. There is a battery, there is a driving mechanism for the pendulum. Then at any moment, whatever energy is being lost to the damping forces, the equal amount of positive work is being done by the motor on the pendulum. So the pendulum maintains its energy level as well as its amplitude. This is an example of the forced oscillation or the driven oscillation. Another daily life example is the case of a swing. Suppose you are sitting on a swing and your father gives you periodic push. So whatever energy is being lost to the damping forces, the air resistance, the viscous forces, that equal amount of energy your father is supplying to the swing, then your oscillation amplitude will be maintained. I hope you get this. So let's dive deeper into the mathematics of the forced oscillation or the driven oscillation. Here we can see a spring block oscillator which we used in the previous video of the damped oscillation. So on this block there are the forces acting as number 1, the restoring force due to the spring, number 2, the damping force due to the air resistance, and number 3, the driving force F0 cos omega dt. Okay. Using the Newton's second law, we can write its equation of motion. If we look at the solution of this differential equation, we get x is equal to a cos omega dt plus phi. Here you can see the value of phi on the screen. What is a? A is the constant amplitude of the forced oscillation or the driven oscillation. And what is omega d? Omega d is the angular frequency of the driving force or the driving agent. Okay, I request you to note it down up to here, and then we'll go into the details of this amplitude. We'll be deriving the conditions of the resonance from this expression. Let's take up the case 1, the ideal situation we are considering, in which the B is equal to 0 and the angular frequency of the driving agent or the driving force is almost equal to the natural angular frequency of the system. Okay. In this case, what will happen to the amplitude? Check it once. Amplitude is f naught by root of B is 0. It means this term vanishes. And since these two terms are pretty closer, so this term will be very small, almost tending to 0. If this term is tending to 0, the amplitude will tend to infinity. Do you get this? Okay. In this case, actually there is no damping. So whatever energy is being supplied by the driving agent or the driving force, that energy will keep on increasing the amplitude of the oscillation. Do you agree? There is no damping, there is no energy lost to the frictional forces or the damping forces. Since the energy is continuously increasing because of the positive work done by the driving force, the amplitude will tend to infinity. This is an ideal case. It will never actually happen. Here we are taking up case 2. The damping is present. So B is not equal to 0. And omega d, the angular frequency of the driving force, is close to the natural angular frequency of the oscillator. Then what will happen to the amplitude? As we know the formula, f naught divided by root of, now I am putting up the values. These two parameters are pretty close. So this term is almost tending to 0 and you can neglect it with respect to this term. Then the amplitude is almost equal to f naught by omega d b. Clear? Smaller the damping constant, larger will be the amplitude. So this is the maximum value of the amplitude for a system in which the omega d is almost close to the natural angular frequency omega. Okay. You can see a curve here in which we have taken all these cases. I'll explain the details of the curve after explaining the third case. Okay. You may note it down, then we'll take up the third case, the last case. Here we have the third case, the last one. The B is not equal to 0 and omega d is far away from the natural angular frequency of the system omega. In that case, we check the amplitude again, f naught by root of m square omega dB square. Okay. Now, B is not equal to 0 and we are taking the B is small. Then this term will be negligible as compared to this term. In that scenario, the amplitude will come out to be f naught by m omega square minus omega d square. Getting this? This term is negligible. Now, let's talk about the resonance. Here you can see the expression of the amplitude again, and I am taking the ideal case where the damping is absent and the omega d is very close to the omega. Okay, then the amplitude will approach towards the unbounded value, very large value, infinite. Getting it? This case is practically not possible. So if you want to write the definition of the resonance, it's pretty simple. Whenever the angular frequency of the driving force is close to the natural angular frequency of the oscillator, the amplitude of the oscillator attains its peak, attains its maximum value. That condition we call as the resonance. Okay. The practical systems, B is not equal to 0, the amplitude will never attain infinitely large values. Amplitude will never be unbounded. Amplitude will always be bounded. Okay. Look at the resonance curves. For the damping cases, the peak of the curve shifts little bit to the left, and if the damping is very large, there is no resonance. Getting it? Almost energy of the system is lost as quick as possible, and then system won't even oscillate. So there is no resonance. I hope it's clear to you. Note it down, and then we'll be taking up numerous good examples of the resonance. Now we'll see numerous beautiful examples of the resonance. I'm taking up the first example from the childhood memories. When you were bored out in the class, you took the cap of the pen and then you tried to whistle. What happens? There is a particular intensity of the sound. You again try something else, a different mode. There is another different intensity of the sound. But suppose the frequency of the driving force matches with the natural frequency of this system, then the amplitude will be maximum and we will get the maximum possible intensity of sound. Pay attention, I am doing that. You got it? I hope you all have tried this case of the resonance in your childhood. Although these systems may have more than one natural frequency that you will read in the chapter Wave on the String. A guitar string has more than one natural frequency. These kind of air columns you will read in the chapter Sound Waves have more than one natural frequency. The building in which you are right now has more than one natural frequency. Got it? At the resonance, the driving agent transfers the maximum power to the system. Okay, that's why the amplitude is maximum. And above or below the resonating frequencies, the power transfer by the driving agent is lower than the power transferred at the condition of the resonance. Do you get it? Taking up the second beautiful example of the resonance. Suppose you are on the swing. The moment you reach at the extreme position, your father gives a push to the swing. Then your oscillation amplitude will increase. Your father steps little bit back, and the moment you reach here, father again gives you a push. The amplitude of oscillation will further increase till you reach here. The father again goes back and then give you another push. If the frequency of the pushes matches with the frequency of the oscillation, feel about it. What will happen to the amplitude of the oscillation of the swing? The correct answer is amplitude will keep on increasing. Will it ever go to infinity? The answer is no. Reason? Ever present damping forces. There will be the friction in between the moving parts of the swing. There will be the air resistance. So although amplitude can increase to a great extent, but it will never go to unbounded value, the infinite. Taking up another example. Look at the destruction caused by the earthquake. The highway is broken from various points, but the nearby buildings are intact. Now I think you can easily explain the reason. If the frequency of the seismic waves is far away from the all natural frequencies of these buildings, their amplitude of oscillation will be pretty small and there will not be much damage to them. Okay, but the frequency of this bridge matched with the frequency of the seismic waves. So large amplitude of oscillation and then bridge shattered. Got it? Now, after that earthquake, to avoid such incidences, they are installing the dampers into the bridges. You can see this picture and you will find some dampers in the bridge. Okay. Another beautiful example of the resonance. You will find many videos on the YouTube where they can shatter a glass using the sound waves. If the frequency of the sound wave is matching with one of the natural frequency of this glass, after some time the glass will shatter down into the pieces. It's an interesting phenomenon to watch. You search it on YouTube, you'll get numerous videos. Okay, and one link I'm sharing in the description from the MIT. There is a beautiful video about it. The next example of the resonance. Now you can easily explain why the soldiers are ordered to go out of step while crossing a bridge. Because if by walking of the soldiers the driving frequency matches with the natural frequency of the bridge, it might shatter down into pieces. Another real life example of the resonance, you can see here an old footage of the Tacoma Narrows Bridge. The year 1940, the winds set up the bridge into the oscillation because the frequency of the winds is matching with the natural frequency of the bridge. And you watch carefully what is happening. The bridge is oscillating like anything, and after some moments the central span of the bridge is falling into the river. So nowadays engineers take great care in designing the bridges or the buildings or any kind of structures. They examine all possible frequencies of the oscillation of that particular structure and try to keep it different from the frequencies of the winds there or the frequencies of the seismic waves. That way they can keep the structure safe. And in addition to enhance the safety, the dampers are also installed in such structures. Got it? Another example of the rattling vibration at a particular speed of a vehicle. The explanation is simple. When the frequency of the engine matches with the natural frequency of the oscillation of the windows or some other parts of the vehicle, then they oscillate at a greater amplitude, and then there is this discomforting noise. I hope you have felt that in your school bus, old school bus. Okay. Another example, sometimes let's say few guests are at your home and you are carrying the beverages to them. While you walk, some liquid spills out of the glasses. Can you explain why? The reason is simple. If your frequency of movement is matching with the oscillation frequency of the liquid, the amplitude of oscillation of liquid will increase and liquid will spill out. Okay. Taking up another beautiful example of the resonance, here we can see 5 pendulums. They are tied to the same string. Now I take the pendulum 1 out towards you and release it. Then the pendulum 1 will oscillate like this. What will happen to the remaining pendulums over the period of time? Pause the video here, think about it and let me know in the comment box. I hope you all got the correct answer. All the pendulums will start oscillating initially because they all are connected to the same thread. So the energy of the pendulum 1 will get transferred to all the pendulums. Every pendulum will be initially oscillating with its natural frequency, but those oscillations will damp out because of the ever-present damping forces, the air resistance, the frictional forces, etc. Okay. Gradually, the frequency of oscillation of every pendulum will become equal to the frequency of oscillation of pendulum 1. Although the amplitude of oscillation for pendulum 2, pendulum 3 and the pendulum 5 will be small, and there is the resonance in between the pendulum 1 and the pendulum 4. Why? If you check carefully, the pendulum 1 and pendulum 4, they are identical. Their natural frequency is same. So the energy gets transferred from the pendulum 1 to pendulum 4 and its amplitude gradually increases. Then the energy gets transferred from the pendulum 4 to pendulum 1 again. Getting it? And this cycle keeps on repeating. After a long period of time, all the pendulums will come to rest because their mechanical energy is lost to the friction, the air resistance, the damping forces. I hope you understood this. If you wish, you may note it down and then we'll go further. Similar examples are present in the electronic circuits. Suppose you have some FM receiver. In the room, there are so many electromagnetic waves reaching, but in your FM receiver, you choose a particular frequency, and related to that particular frequency, the amplitude of the sound is maximum. So that sound will be clearly audible, remaining all oscillations damp out, die out. I hope you understood this example. So now for your practice, here is a checkpoint. You may pause and you may try all these questions for better conceptual clarity. Then I'll be simplifying to good questions and will present the answers of all checkpoint questions. Got it? I hope you are done with all questions of the checkpoint. So here is the first question which I am going to solve. If you wish, you may pause and give it a try. Its calculation is pretty simple. I hope you got the correct answer of this question, which is 9 meter per second. So we can see the solution here. Reading the language of the question, we know that the resonance will happen when the driving frequency is close to the natural frequency of the system. Do you agree? And for that computation, we'll use this formula: speed is equal to distance divided by time. Looking at the language of the question, they are asking you the speed. Distance is given as well as frequency is given. Frequency is 1 upon time period. So we can write this as distance into frequency. Do you agree? Distance is given as around 10 meter. Frequency is given as 0.9 per second. So the answer will come out to be 9 meter per second. Clear? Why the word about has been used in the language? If you remember our initial discussions in the theory, this is a practical system. Practical system means there is some damping present, and if damping is present, for resonance these frequencies are close, they are not equal. Got it? So they are using the word about. So this is the answer. I hope you understood the question. Note it down, then I'll take up the last question of this video. Here is the last question of this video, simple formula based question. So if you wish, you may give it a try, and then I'll be simplifying the things on the board. I hope you are done with your calculations. So I am simplifying the first part, the resonance angular frequency of the system. So omega will be equal to root of K by M. K is given to us 20 and the mass is given as 2 kg. So it comes out to be 3.1 per second. Is it okay? Now solving for the second question. The angular frequency of the driven oscillator. So omega of the driven oscillator will be actually equal to the omega of the driving force, and omega of driving force is already given, which is equal to 2 pi. So it will be 6.28 per second. Is it okay? Now going for the third part. The third part is asking us the amplitude of the oscillation. So let us utilize the formula. Amplitude is equal to F naught divided by root of m square omega square minus omega d square whole square plus omega d multiplied with b and then whole square. This is the function. This is a case of a damped oscillator or undamped. Looking at the language, we know this is undamped. Undamped means this b part is 0. So this term vanishes. Feed all these values in this expression. You will get the value of amplitude 5.09 centimeter. Now you will be observing the solutions of the checkpoint. Stay awesome and do report few cases of the resonance from your daily life in the comment box.